This is lecture 14, and in today's lecture we'll be continuing on the idea of Lewis structures. Specifically today we'll be talking about a lot of ways that they fail us and ways that they start to break down. So we'll be talking about exceptions and specifically talking about formal charge and resonance. Let's start today's discussion with ozone. This is O3. You might have heard of the ozone layer that's really high up in our atmosphere. It's a region with a lot of ozone in it. So how would we draw the Lewis structure for O3? Well, it turns out there's two possibilities. So you're going to have a central oxygen in either of these, and it's going to be double bonded either to the oxygen on the left, or it's going to be double bonded to the oxygen on the right. And we're going to ask which of these is correct. And you can actually think of this kind of as tumbling through space and looking the same, but it turns out that the correct answer for this, of which is correct, is that both of them are sort of correct. Or more accurately, neither of them is correct. They're both just approximations of something that's a little more complicated. What's really going on here is we're going to have some amount of both of these. So when you have more than one possible Lewis structure, we draw resonance structures. So up here I have two resonance structures, or two possible resonance structures, and we put this double-sided arrow in between them. Now normally this double-sided arrow in chemistry means that we're going back and forth between these two. However, when it comes to resonance structures don't actually exist. So ozone never actually exists in one of these states or the other. In reality, it's going to be a weighted average of both of these structures. So they're both going to be contributing to the true structure. So what we see in real ozone is oxygen-oxygen bonds on either side of the central atom that are exactly the same in length. So they're both about 1.28 angstroms. And if we look at the electron density on this molecule, and this is our heat map of electron density, the blue region in here indicates low electron density, and the yellow and red indicates region of high electron density. And so in ozone, we actually see -1/2 charge. So this isn't a full formal charge, but this is a partial charge that we'd signify with a lowercase delta. But we see a strong partial negative charge on both of these kind of our wing oxygens here. So what this is really doing in terms of a Lewis structure is something more akin to this, where the central atom has a single bond to both side atoms, and then that double bond is actually delocalized, or it's spread out between all three atoms. And so with delocalization, this happens in molecules where now we have an orbital, a bonding orbital, that's got a much different shape. It's spread out now to encompass all of these. So in this case, we're going to say we have a bond order that's not 1 and not 2, but somewhere in between 1 and 2. And so now we're saying bond order is getting a little more complicated. And we're not actually going to think about this as a double bond going back and forth. And actually, I'll backtrack a little. We will use terms like this double bond flipping back and forth here, but in reality, it's not happening. In reality, we just have this delocalized bond that's not changing shape. So first, let's talk about bond order. How do we figure out the bond order in a structure like this? It's actually not too complicated. So the first thing you're going to do is basically count the number of bonds in this delocalized region. So this double bond right here, we have shown in our resonance structures is kind of flipping back and forth, which means it's really delocalized over this area. But so we have two single bonds that are static, and then we have this delocalized double bond over all of here. So we have 3 bonds in total. In other words, we have 3 pairs of bonding electrons. And how many positions? Well, there's 2 positions here. So we're going to do 3 pairs of bonding electrons, or 3 bonds, divided by 2 positions. So it's going to have a bond order of 1.5 on each side. So It's going to look like this. So if we can do this, if we can draw these structures, and we have a way of drawing them, why do we even bother drawing these resonance structures in the first place? If these aren't real, if they're not really meaningful? Well, the answer is that they're very useful for ease of understanding, for communicating what's going on in these molecules. So it's easier to determine the bond order when we have these resonance structures, and it's easier to count electrons, make sure our bookkeeping is good, and to determine the behavior of the electrons. So here I'm showing a very simple structure where this double bond is just delocalized over 2 bonds, but these actually get much more complicated. Here I'll show you a medium complexity molecule. So benzene is actually a 6-member carbon ring. So we've got carbon at each one of these corners here, and on each of these carbons we have a hydrogen sticking off. So you'll notice there's quite a bit I'm leaving out. But often we'll draw benzene like this on the left, where we have these double bonds here in 3 specific locations. And we'll draw that because it's a simple way of describing what's going on, but you'll notice it's also technically false. Really what's going on is something that looks like this. Now here you might think, oh, well, we have 1 double bond delocalized here, 1 delocalized over here, 1 delocalized over here, but that's actually not accurate either. In benzene, what you actually have is 3 of these double bonds, or as we'll call them later, pi bonds. You have 3 pi bonds, all of which are delocalized over all 6 of the carbons in here. So delocalization actually gets very complex. And once we start getting into actual molecular orbitals, or the orbitals that we see in molecules, you'll see that it's actually even worse than this. It gets to a point where it's too complicated to learn, at least in this class. All right, well, let's back up and just talk about the rules for drawing our resonance structures. So the first rule is you're still just going to draw a regular Lewis structure. And then when you notice there's a region where you could have some ambiguity where you put the pi bond, that's usually where you start thinking, oh, there's going to be some resonance here. And so when you're drawing your resonance structures, you're going to keep the same Lewis structure. All your atoms are going to stay in place. You're really just going to be moving lone pairs and double or triple bonds. So electrons are all that get to move here. You don't get to move the atoms at all. And you want to make sure each of your resonance structure has the same net charge. You don't want to have one structure with one charge, another with a different charge, because then you're adding and subtracting electrons, which isn't what's happening here. Really what's happening is we're trying to describe the motion or location of these electrons. So for practice, let's look at the Lewis structure for carbonate. So this is CO3 2-. The 2- tells us that we get 2 extra electrons in addition to the valence electrons that carbon and oxygen are bringing us. So if we draw the Lewis structure for carbonate, we actually get something like this, where carbon is double bonded to 1 oxygen and then singly bonded to 2 other oxygens. But which oxygen is it going to be double bonded to? Well, we're actually going to draw 3 resonance structures here. We're going to say that it's got some double bond characteristic with each oxygen. So then what is the bond order here? Well, then we're going to have 1, 2, 3, 4 bonds spread out over 3 locations, and so it'll be a 1.3. All right, let's see if you can practice this. What I want you to do is first draw me a Lewis structure for NO2-, and then figure out how many resonance structures are there. Go ahead and pause now. Okay, these should be the 2 resonance structures you got. So we have nitrogen double bonded to 1 oxygen, single bonded to the other. And then we're going to draw the other resonance structure where it's reversed. So how many resonance structures does it have? It has 2. All right, now here is another question regarding this delocalization. What is the CO bond order in carbonate? So this is CO3 2-. I've got our 3 resonance structures there. Go ahead and pause the video and try and figure it out. All right, so we have 1, 2, 3, 4 bonds that I'm counting there, and the double bond we have drawn in 3 locations. So that's another way of thinking about it. How many locations have you drawn this in, and how many bonds are there total? So we have 4 bonds or 4 pairs of bonding electrons divided by 3 positions. So you should get a value of 1.33 here. Now this gets a little more complicated when we aren't just dealing with atoms like this, where we have one central element and a different element that it's resonating with, or some sort of symmetric system. So often you'll have asymmetric systems, and in that case, all the resonance structures are not going to contribute equally. And actually this can happen when you even have a symmetrical case. So let's look really fast at carbon dioxide's Lewis structure. So carbon dioxide has a Lewis structure that looks like this. We've got carbon in the middle, it's double bonded to both oxygens, and both oxygens have a lone pair. Well, it turns out this isn't the only way you could distribute all of these electrons. You could also distribute them in these 2 patterns, right? Where carbon is triply bonded to one oxygen, singly bonded to another. And in these cases, each atom still has a full octet. So this oxygen on the left, it has 1, 2 electrons over here. It's got 1, 2, 3 bonds, which is 6 electrons. So that's got 6, or sorry, that's got 8. Carbon has 4 bonds, which means it has 8 electrons. Oxygen has 1, 2, 3 lone pairs and a bond. So that's 8 electrons as well. But all of these structures aren't contributing equally to the true structure of carbon dioxide. So now we have to figure out which one best represents the molecule, and if there's any amount of weighting that's going on there, as far as is one more important, are we going to weight it more than others? And really, how do we know? How do we know which is the most important? Well, the first tool I'm going to give you in thinking about this is what we call formal charge. So you remember in partial charge, we're not getting a full positive or negative number. Well, here in formal charge, we're actually going to say, all right, in this structure, this atom would have a full positive or negative charge. And in these guys, we're going to be counting electrons to do that. So really what we're doing is balancing protons with electrons here. But there's a simpler way to think about it mathematically that gets you the right answer. So the way we're going to calculate formal charge is we're going to ask how many normal valence electrons does this element have. So for example, oxygen normally comes with 6 valence electrons before it's combined with something else. So we're going to take the normal number of valence electrons. We're then going to subtract the number of lone pairs, or sorry, the electrons in lone pairs, and subtract 1/2 of the electrons in bonds. So for example, oxygen here is starting with, or it normally has 6 valence electrons, then it has 1, 2, 3, 4 electrons in lone pairs. And then, so now we're down to 2 of those normal valence electrons. We have 2 bonds. We're going to have, so we'll have 4 bonding electrons, but we'll have to divide that in half to have 2. And so overall, our oxygen will have a formal charge of 0. That'll be true of this other oxygen here, and it'll actually be true of carbon in the middle, though I didn't do the math for you right here on that one. Okay, so now they're all 0. What happens if instead of having 2 lone pairs and 2 bonds, if one of these lone pairs now is changed to a bond? So now another way of saying that is this oxygen, it normally comes with 6 valence electrons. We have 2 electrons as lone pairs. So now we're down to 4, and then subtract 1 for each bond. So minus 1, 2, 3. Now we're down to a 1. So we have a 1 plus on that oxygen. And then for the other oxygen that's now lost its double bond and gained a lone pair, it actually has a formal charge of -1. And as you can imagine on this other molecule, the charges are very similarly arranged. Okay, the best Lewis structure of all of these is going to be the one that minimizes formal charge on all the atoms. So in this CO2 structure with 2 double bonds, everything has a charge of 0. So we're going to be much happier with this structure than we are with either of these other 2 structures. which means that this guy is going to be the most favorable. Now, you can't always get the charge down to 0, especially if you have a charged anion. If you have extra electrons in there, you're never going to get all of the atoms down to 0. So when it's unavoidable, you're going to try and put your negative charge on the most electronegative atoms available. And that can be a little tricky, but I think you'll get a hang of it. Now let's try this iCLICKER quiz real fast, see how you're doing with all this stuff. I want you to give me the formal charge on this phosphate atom, or sorry, this phosphorus atom in the middle of phosphate here. So phosphate is our PO4 3- structure. So go ahead and try and calculate that for me. Okay, so phosphorus normally comes with 5 valence electrons, right? It's 3 spaces away from the noble gases, so it's normally coming with 5 valence electrons. But it only has 1, 2, 3, 4 bonds and no lone pairs. That means it's going to have your 5 normal minus your 4 bonds. You're going to be left over with a 1. So you're going to have a 1+ charge. In other words, it's normally got 1 electron there, and now it's for whatever reason missing. So in this structure, the way I've drawn it here, the central phosphorus atom is going to have a +1 formal charge. And then all the oxygens are going to have a -1. So if you add all this up, a 1 plus minus 1 minus 1 minus 1 minus 1, you get a total of 3 minus. So that all works out charge-wise. Now this structure, though, actually is not the best because we have a distribution of charge where we don't have to have it. So the more common structure for the phosphate ion, the much more common way of drawing it is like this, where one of the oxygens has a double bond to phosphorus down here. And then we have only 3 negative charges and 2 atoms with 0 charge on it. And then, of course, we're going to get this double bond actually delocalized over all 4 of these PO bonds. Now, looking at that, you might say, well, hold on. Now phosphorus has 1, 2, 3, 4, 5 bonds, which means it's broken its octet. Well, that's true. And we'll get into that in a minute. There are cases where we break the octet. But let's start first by talking about how we can use the Lewis diagrams to predict structure, or this idea of formal charge to kind of tease out which is a more likely structure. So for example, if I have laughing gas, N2O, is that going to be arranged as N bonded to O bonded to N? So oxygen's our central atom, or is there going to be a nitrogen as our central atom? So one way to figure this out is to try and draw Lewis structures for these guys. So if I have oxygen as my central atom and I've distributed all my valence electrons appropriately, then it's actually pretty hard to draw a good structure where oxygen only has a single bond. And in all of these structures, you'll notice oxygen has a +2 charge on it. Now that's not allowed because oxygen is super electronegative. There's no way it's going to be existing as a +2 charge in a molecule. So let's try now rearranging it and using nitrogen as our central atom. So here we have our N double bonded to an N double bonded to an O, and we've got a couple of resonance structures where we've got a triple bond on one side and a single on the other. Now, if you look at the charges on these structures, we do have one structure that has a -2 charge on a nitrogen, but overall, all the charges on all these structures are a lot lower than they are for the NON structures, right? And so the NNO is actually the more favorable, or is the actual favored structure for N2O. This NON molecule really doesn't exist, right? So this is a case where we're violating that symmetry rule that I tried to teach you last time. And the reason we have to violate it in this case is to minimize formal charge on all of our atoms. And then we can take this a step further, though, and say which of our NNO resonance structures, so which of these resonance structures are contributing the most to the delocalized structure? Well, the most important structures are going to be the ones with lowest formal charge on most things. So this far right guy has a -2 on that nitrogen and a plus on the central nitrogen and a plus on that oxygen. So that's not going to be very favorable. These other two each just have a single positive and negative charge. So these two are going to be more favorable. And we could take it a step further and ask which of these two is more favorable as well. And then we're going to start thinking, well, which one has the negative charge on the more electronegative species? Oxygen is more electronegative, so we would tend to consider this structure as being more dominant. Now, when I show you this, though, you might be a little surprised to see that the bond order here between this nitrogen and oxygen is slightly more than 1.5. So it's more than just this single bond average with this double bond. You actually are averaging this single with this double with this triple, and somehow that average comes out to be 1.6. So you'll notice if you take 1 plus 2 plus 3, that's 6. You divide that by 3, should get an average of 2. But since this structure is much more favorable, it's going to bring the average way down from 2 all the way down to 1.6. And then this region right here, this double bond structure is going to be averaging with the triple bond and the single bond, but it's much closer to the triple bond here. So it's at 2.73 rather than at 2 or something. And you might also notice now that the bond order here is not adding up to whole numbers. So if I take 1.61, add it to 2.73, that's not equaling 3 or 4, right? That's equaling 4.34. So now we're not even getting whole numbers. And the reason for that is because now even these lone pairs are kind of getting involved here. So the takeaway here is that formula I taught you 2 minutes ago for calculating the bond order of these resonance structures, it's actually just an approximation. So use that calculation to get approximate values, but they're definitely not real values. So they're more close than just choosing whole numbers. But keep in mind as you're calculating with that it's just an approximation. You're not going to have to figure out these bond orders to, 3 decimal places or anything like that. With that, though, let me ask, what is the most important resonance form for the cyanate ion? So cyanate is OCN-. I have our 3 dominant resonance structures here, and I want you to figure this out. So you want to keep in mind formal charge and electronegativity. All right, so if you calculated the formal charge on all of these, so for carbon in the middle here, it's always got just 4 bonds no matter where they're attached, so it's always going to have a formal charge of 0. But the oxygen and the nitrogen, they're changing whether their electrons are in bonds or as lone pairs, and so that's going to affect their formal charges. So I'll just write out these formal charges here. If you have questions about how I got these, let me know. What you'll notice is for A and B, each of these just have 1 atom with a formal charge of -1, and C has 1 atom with a +1, 1 with a -2. So C is not going to be favorable at all. And then we have to decide which of these, A or B, is more favorable. And the way we're going to decide that is using this negative charge right here. The negative charge is going to want to spend more time on the oxygen, or in other words, the delocalized bond here is going to favor having more electron density on the electronegative species. Oxygen is more electronegative than nitrogen, so A is going to win out. It's going to have the lowest formal charge on all the atoms, and it's going to put its -1 on the most electronegative atom. All right, so far we've just been talking about formal charge and how that affects resonance and delocalization and so forth. Now let's get into some rule breakers, things that break our octet rule. And we'll start with the low electron rule breakers. So this is NO, this is nitrogen monoxide. Nitrogen monoxide has a Lewis structure that looks like this. So nitrogen is double bonded to oxygen. Oxygen has 2 lone pairs and 2 bonds, so it has a full octet. But nitrogen it has one lone pair and a double bond, but it's also got this unpaired electron up here. Now, if you calculate the formal charge on both of these atoms, they actually both have a formal charge of 0. So they're both perfectly fine with this arrangement, and the structure would be reasonable except for that electron right there, that unpaired electron. So this type of structure is what we refer to as a free radical. A free radical is a molecule that has an odd number of electrons. So that's always going to result in it having one unpaired electron. So a free radical has to have an odd number of electrons to form. And these guys are usually very reactive. That electron wants to pair very badly, and so this will form bonds very quickly. Okay, so that's a rule breaker in the form of not having enough paired electrons. But let's say all of our electrons are paired, but we still don't have an octet. So BF3 is a molecule I've shown you before. So boron really just likes to form 3 bonds. So here in BF3, its Lewis structure is going to look like this, where each of the fluorines has 6 electrons in these lone pairs and a single bond. So you could actually draw a structure where there's a double bond between boron and this fluorine. And in this structure, actually everything has a full octet. Everything has, or is pretty happy here. But in this case, you have a formal charge of -1 on the boron and a +1 on the fluorine. And fluorine is very electronegative. It's not going to be happy with this. It's not going to be happy seeing boron with some negative charge. And so this structure actually doesn't happen, or doesn't contribute very strongly at all. So boron with 3 bonds is more common. So molecules that don't achieve a full octet atoms that don't achieve a full octet in molecules really is limited to beryllium, boron, and magnesium. And boron's the one you'll see the most, primarily because it's a nonmetal that likes to bond to things. The reason that beryllium, boron, and magnesium behave this way is because they're all relatively small and they're not very electronegative. And so they're just not going to have the strength to pull more electrons to themselves. So they're kind of stuck in this middle realm where they're just always never quite achieving everything they want in life. Okay, so now we've covered radicals and these 3 guys that can achieve a full octet. Let's go beyond the octet now to some rule breakers that get what we call an expanded valence shell. So this is the structure for SF4. So in this case, all of our fluorines still have 6 electrons tied up in lone pairs and a single bond to the central sulfur. But if we look at the central sulfur, it's got 1, 2, 3, 4 bonds and a lone pair, which means it's really got about 10 valence electrons. So we're now saying it's got more than 8 electrons in its valence shell. And this is what we call an expanded valence shell. So atoms beyond the n=2 level, so things that show up on the 3rd level or the 3rd row on the periodic table, can have these expanded valence shells. Now, just because they can doesn't mean they're always going to. But this happens because these larger atoms, they're bigger and they have more room around them basically to fit things in. And usually you get this happening when you're bonding to something with a strongly electronegative element. So like if you're bonding to fluorine, oxygen, or chlorine, so like if in SF4, these fluorines are each pulling fairly hard on these bonds. And so you can almost think about this as sulfur on average having 8 valence electrons. That's kind of a watered down view of it, but it's something that works. And actually sulfur often forms a complex with fluorine called SF6. And in that case, sulfur then has 6 bonds with no lone pairs. So then it has 12 valence electrons. And SF6 is fun because if you breathe it in, it actually makes your voice super low. Whereas helium makes it high. I'm not very good at high voices, but I'm good at low voices. But let's talk about this expanded valence shell or expanded octet idea. And let's ask the question, when do you get to expand the octet? When you're drawing a Lewis structure, when do you get to do it? And the answer is whenever you need to. Whenever you have to expand the valence shell, that's when you're going to do it. And again, this is really going to just happen with the n equals 3 row and down on the periodic table. But let's look at SF4 for a good example. So with SF4, if we count how many valence electrons each of these is coming in with, sulfur is coming in with 6, each of the fluorines is coming in with 7, so we have a total of 34 valence electrons here. And if we look at the ideal, how many electrons we'd need for each of these to have an octet by itself, that would be 8 times 5 or 40. So 40 electrons is our ideal, 34 is our reality. So if we compare those, that would mean that we'd have 6 electrons, or there's a 6 electron difference. If we divide that by 2, that would tell us that we need 3 bonds to make this molecule happy. Okay, but you can't combine 5 atoms with only 3 bonds. You need at least 4, right? You need sulfur to at least attach to each of those elements individually. So you can't get away with just 3 bonds here. So then you're going to have to expand the valence shell. Otherwise, this just isn't going to work. And you get the structure that we were just looking at on the previous slide. All right, let me give you a little practice with this. And I want you to tell me which of the following following molecules or salts contain an atom with an expanded octet. So to figure this out, you're really going to have to draw the Lewis structures of each of these species. Go ahead and pause the video and do that. All right, I'm not going to go through how to draw the Lewis structures since we've covered that a bit in the past, but here are all of the Lewis structures just in order. So for the top one, we've got fluorine. It's got 8 electrons around it, and the other fluorine does as well. 8 is oc, so they've got a full octet. Magnesium, its electrons have been stripped away. Getting stripped away is the opposite of getting an expanded octet, so it's none of those guys. Let's look at the carbonate ion. So here we have carbon in the middle. It's got 1, 2, 3, 4 bonds. It's normally coming with 4 valence electrons, so it's fine right there. It's got 1, 2, 3, 4 bonds or 8 electrons around it. This top oxygen has 1, 2 lone pairs and 2 bonds. So add that up, we've got 4 electron regions or 8 electrons on that top oxygen. One of these side oxygens has 1, 2, 3 lone pairs and 1 bond. That's 4 electron regions, still a full octet. And so remember with CO3 2-, we have these resonance structures, but the octets that we just counted for the first resonance structure are going to be true for all the others. So CO3 2-, nothing in there has got an expanded octet. With SH2 or H2S, we've got sulfur in the middle with 2 lone pairs, 2 bonds, so that's a full octet. Hydrogen obviously doesn't have an octet, but it has 2 electrons in its valence shell. That's not an expanded octet, that's the normal state for hydrogen. Now let's get down here to xenon F4. You might be tempted to say, well, it's not this one because it's a noble gas. But actually, this is a real molecule. So in this case, xenon has 1, 2, 3, 4 bonds and 2 lone pairs. That's 6 of these electron regions. So 6 times 2 would be 12. So this actually has 12 valence electrons. So xenon F4 or XeF4 has our expanded octet. So that's most of what we're going to talk about today with these exceptions and rules. So we're just going to finish off with some fun trivia about the noble gases. So we talk about these noble gases as being unreactive or unresponsive. And that's not exactly true. It's still mostly true. But as early as 1962, a Canadian guy named Neil Bartlett started forming the first xenon compounds. And so in these xenon compounds, he just got it to finally react with fluorine. So he was able to make XeF2, XeF4, and XeF6. Right down here, I've got some pictures of some crystals of XeF4. These are really stable at low temperatures. But these aren't actually the only structures of noble gases or noble gas compounds that have been discovered. So krypton was actually also eventually made to react with fluorine to get KrF2, and that's the only known stable krypton molecule, or the only stable molecule containing krypton that we know about. And argon was eventually made in 2000 to form this compound, HARF, or HARF. That's not really what anybody calls it. Kind of looks like a sandwich. This is only stable at low temperatures. And actually, I'll have to revise my statement here about the KrF2. You can actually also get KrF. And so the last group of these that we've seen are just noble gases complexed with a single halogen. So for example, KrF or XeCl. In these species, there's just a couple of them. And these are really useful in lasers and generating laser light for reasons that are way beyond the scope of this class, but pretty interesting science. So are noble gases unreactive? I would still say yes, they're mostly unreactive. This is just about all the compounds that they form. If you go to the Wikipedia page for the noble gases or the noble gas compounds, it might give you, I think it gives you a couple more than this, but really there's just a couple and they're kind of hard to make. Anyways, let me know if you have any questions or concerns about any of the stuff we covered today. And I look forward to seeing you later.